This conference will now be recorded.
All right. Hello, everyone. Welcome to SECOORA's webinar series, Coastal Observing in Your Community. SECOORA is hosting this webinar series to discuss, highlight, and raise awareness about coastal ocean observing activities in the southeastern United States and beyond. My name is Emily Noakes, and I am SECOORA's communications specialist. I will be moderating the webinar today. So today we are going to be hearing from Dr. Leila Hashemi-Beni from the North Carolina Agricultural and Technical State University, or North Carolina A&T University. She will provide an overview of rapid floodwater mapping and depth analysis using optical UAV and SAR technology. And like I mentioned before, this webinar is being recorded and it will be available on our YouTube channel at the end of this week. So first, I want to provide a brief overview of SECOORA for those who may not be familiar or may not have ever attended one of our webinars before. SECOORA is the regional coastal ocean observing system for North Carolina, South Carolina, Georgia, and Florida. We aim to collect data and create tools that support human populations, coastal economies, and a healthy, sustainable environment. We are one of 11 regional associations that make up the Integrated Ocean Observing System, also known as IOOS. Our mission is to bring people, technology, and data together to facilitate collaborations, projects, and knowledge sharing to ensure coastal ocean resilience, safety, and a thriving blue economy. If you would like to learn more about us, please feel free to scan the QR code here to be directed to SECOORA's newly designed website, SECOORA.org. You can also search SECOORA on Google and we should pop up. So I wanted to go over a couple of quick announcements before we get into the meat of the webinar while I have you guys captive. We have a funding opportunity that is open right now, and we are inviting proposals for funding the installation of new surface elevation table stations, or SET stations. And this also includes the reactivation of historic SET stations within our region. So North Carolina, South Carolina, Georgia, and Florida. This opportunity will cover the cost of materials and supplies, which SECOORA will purchase and ship directly to you. So please email communications@secoora.org if you'd like more information, or you can visit the opportunities page on our website, which will lay out all of the proposal requirements and deadlines. And we have a coming soon announcement. We will be opening up our student awards in mid-September, and these opportunities are open to both undergraduate and grad students, in addition to early career professionals. Keep an eye out on our social media for updates, or you can join our listserv by shooting me a quick email at communications@secoora.org to let me know that you're interested in staying up to date. We also have a ton of information about these two opportunities on our website if you'd like to learn more. The first is called the Bamboo Ocean Scholars Award, and the second is called the Data Challenge. All right, so now that everybody is super familiar with SECOORA, let's get into the webinar. During the webinar, we highly encourage you to ask questions to our lovely presenter. Please enter your questions into the chat, and with time permitting, we will have a Q&A session at the very end. And if we run out of time, or if you think of a question at the very last minute, please feel free to send me an email, communications@secoora.org, and I will get you your answers. So we are very excited to be hosting Dr. Leila Hashemi-Beni for this month's webinar. Dr. Hashemi-Beni is an associate professor of remote sensing and GIS at the Department of Built Environment at College of Science and Technology within the North Carolina A&T State University. She is the director of NCAT's DEAP Institute of Geospatial Data Science and Remote Sensing for Environmental Management, funded by NASA. She works as a PI/co-PI on many projects supported by NASA, NSF, NOAA, Microsoft, North Carolina Collaboratory, North Carolina DOT. She is the co-chair of Laser Altimetry and Sensor Integration Working Group, excuse me, International Society of Photogrammetry and Remote Sensing. I will now turn the reins over to Dr. Hashemi-Beni, and you should be able to share your screen.
Thank you so much, Emily, for the nice introduction. So I'm sharing my screen. Can you see my screen?
Yes, I can see your screen, and now it is full screen.
Okay, great. So good afternoon, everyone. I'm very glad to be here, and I'm excited to share some of the research activity that we're doing in North Carolina A&T State University Geomatics program. So in our remote sensing and geospatial research laboratory, basically we're trying to use best use of the remote sensing data and geospatial, also developing the methods for using this data for the different to protect our environment by providing useful information for landslide monitoring and prediction, for water quality monitoring, land use, land cover classification, precision and small agriculture, natural disaster management, and traffic management. We have also support from the different government and federal and state agencies, and as well as the industry partner to do these projects that make it very kind of make them possible to be done in our lab. So one of the main research focuses is flood mapping. As you know, that flooding is very serious problem in North Carolina, in United States, and in many different countries. So because that cause damages on people's life and also properties. And that has caused more than 850 billion since 2000, and as you see in the diagram, that is accounts for more than 65% of the cost from all natural disasters. So this is an example of the flood mapping. Flood map is very important, and for this reason, flood map is very important to identify the extent and also depth of flood for different reasons, for emergency response, damage assessment, planning, decision making. And it should be accurate and real time to be very effective. This is an example of the flood map created by Boston Harbor in 3 dimensions, but it's based on the hydrodynamic modeling. Those modeling, are very effective, but maybe kind of they are time consuming and can be used for real time scenario. Basically, all of those models, physics model that we call, they are based on the physical, empirical, numerical model. So how we start, we begin with the understanding of the physical system or process, how flood happening. And then we identify event or state or what we want to detect, in this case, flooding. And then we define some hypotheses, we develop methodology, collect data, doing modeling, and then we basically correlate between what we observe and we got with the event that we are trying to detect. So this modeling is very strong because rely on the deep understanding of the system and process. So, and also we can really work on this model is based on the established relationship between variable that is understood very well. But what is the problem of this kind of modeling is, first, those models are very simplified. They can't capture infinite complexity in the system. And also they have problem with the noisy data or the variable that are not included in the models. Also, even if we consider that any robust model, physical model, still they are very computationally intensive. and they are not suitable for performing real-time scenario. And another maybe shortcoming is that this model-driven approach, hydrodynamic modeling, is expensive. Even they are powerful, but they are expensive and take time to develop. They are based on the trial and error approach. That means we start with a theoretic based hypothesis, and then we do the experience based testing, and it go through the loop, and until we can get we need to refine model, and until we get a desirable result. So here maybe one of the research question, how we can go beyond of this traditional model based geospatial data analytics and advance our understanding of complex spatio-temporal event, especially for fast happening kind of event like flood or other different natural disaster. Maybe based on all of those recent advancement in data-driven, we can look at that a new way of thinking that allow AI and machine learning to find the connection between the variables. So we can go include the different variable, and also, but the problem is that they need really big data. They are data hunger. Just they need to have a big data or training data set so they can make a reliable, meaningful result. The reason because it start to extracting pattern and relationship between in the training data set, and so we need to have enough data to have a complete picture of what's happening. Maybe one of the technology that can benefit from the data-driven approach and also can be used for the environmental management is remote sensing. We have a lot of satellite in space that continuously observe our Earth. So we have a lot of free data available. Also, in addition to satellite, we have many other platforms like manned airplane, unmanned, UAV or drones that they can fly in the different flight height and capture data at different resolution. And also we have a lot of sensor that we can install in the field and observe, like the different environmental phenomena that we're trying to monitor. Regardless of what platform we are using, always sensor is most important component of the remote sensing technology, because that sensor basically record and collect data, and like is collect reflectance or backscatter of the earth, land, and water surface. Each sensor working at different range of the electromagnetic. So that means no matter, depend on what sensor we are using, we are looking at the basically the event or phenomena based on the certain electromagnetic perspective. We can have imaging sensor, non-imaging. Example for imaging sensor is creating optical data, synthetic aperture radar or SAR, thermal, altimeter for non-imaging, radiometer, spectrophotometer. So with that introduction, the goal of my research lab is to combine all of the data, multimodal and multi-temporal data, to create a very basically comprehensive and detailed knowledge about the environmental dynamic for both rapid changing events like flood, landsliding, earthquake, forest fire, or for steady progression like erosion monitoring for agriculture. So basically we can use those data with a different perspective, develop a different advanced method to combine them and extract those information. So for that, we started to work on as main focus for my research lab, we started using the UAV data for the detecting flooding using the AI. So our study area was the Princeville and Lumberton during Hurricane Florence and Princeville during Hurricane Matthew. And this was when we started with a project supported with NSF, and also we are working closely with the North Carolina Emergency Management and Geodetic Survey, that they collect very useful information and provide very basically insightful and feedback about those natural disasters, what we need to extract. So we use the LiDAR data that collected by NCEM and high resolution data. And also we use flood gauge reading data from USGS for validation and for developing our algorithm. So we have, using this data, we basically created manually our training data set, and then using the already pre-trained algorithm, like we use FCN, full connected network, convolutional network. So we fine-tune that. Sometimes transfer learning is very helpful. We don't need to always develop kind of architecture from scratch. We can use those already available and be proven to be kind of effective method, and just we fine tune with a small number of the data set that we have for different study area. So this is how we started. We just wanted to know how we, start using AI and deep learning for processing UAV data, drone data for flood management. And then we use some algorithm for the data augmentation to artificially increase our training data set, and then we did prediction to the k-fold cross-validation to make sure that we can manage that a small size sample to create more effective result. And using the confusion matrix, we also did the accuracy assessment. So here is some number that, result that initially we received, we obtained using the deep learning for the flood management using drone data, optical drone data. As you see that we could achieve 98%, accuracy. But this is using the data augmentation. Basically, is increased our accuracy when we don't use data augmentation. But when we're talking about the 90%, basically we are referring to the open water, where we can see water. So basically deep learning could easily detect that in maybe short, very, very fast. But as you see, we have some area covered by vegetation, and we don't know, is it the inundated vegetation or dry vegetation? And why is important? Many of the states in the country, they covered with, they have a lot of vegetated areas, and sometimes we have some flood in those areas that come to the city suddenly and create a lot of damages. So it's important for us also detect those flooding in those areas. But this is not possible with optical data, because optical data can penetrate vegetation. So basically capture just the surface, reflectance. So for that, we try to develop an integrated method that combining the optical data and DTM, or digital train model, that using the hydroflattering concept that water should be basically flat. So we try to use the computational geometry and detect the water in the under vegetation. But the problem is, this is the result of that. Here is the Princeville during Hurricane Matthew, and this the basically ground truth for us, that flood map by USGS. That is initial result that we got from the flood segmentation using just optical data. Optical data is the data that is natural color, right? So as you see, that is very, very different from the ground truth. But when we combine that with the digital elevation model, we increase the accuracy quickly. And that is very promising and is more kind of similar to the ground truth. But why we say promising result? Because they use this map from USGS took time to be created. But for us is matter of less than 1 hour. So for this reason, that those deep learning and data fusion can quickly create initial data for first responder and decision maker, so to know what's happening during the flooding, and is very helpful for the real-time flood monitoring. So, but still, that method for the integrating basically DTM with the deep learning always depend on the quality of digital elevation model. If our digital elevation model, we don't have that, or the quality is not good, maybe we can't get good result. So for this reason, we decided to go with a more reliable approach that we started working on a project that luckily we got the support from NOAA and is funded, that we could we started to work on the fusing the optical data with the synthetic aperture radar data. So they are both basically using the different electromagnetic signal to capture the data. And this is the one of the very effective algorithm, but there are a lot of challenges in the data fusion using deep learning that we are working to that NOAA funded project. In this project is in collaboration with North Carolina Emergency Management and Geodetic Survey, and also in collaboration with SECOORA, that North Carolina Emergency Management team collect data using UAV at different flight height and different sensor, and SECOORA basically make it that data available and doing some, like technical pre-processing on data and send to the North Carolina A&T database. And we implemented our algorithm in Google Earth Engine because it's the data computing in cloud computing environment that make things much faster, and the result go back to SECOORA for for visualization and make it available to the end user. So this is the data management plan that we have. We closely working with our partner, and that is very helpful to develop the research in A&T. And when we're talking about synthetic aperture radar, just for maybe it's very basic introduction about the data, that basically because it's using the longer wavelength for collecting data, it can penetrate cloud, and also they can work anytime during day, night time, and all weather condition. That is not the case for optical data. And also it can penetrate vegetation, depending on what signal we're using, and it can be very beneficial for flood mapping, especially in the dense vegetation cover. But the problem is sometimes we have, because of the backscattering mechanism, sometimes we have problem with the detecting, differentiating between water and water-like surfaces. And also the data normally is very noisy, and correlation and alignment of the data is not easy. It's not friendly, basically very friendly to human eyes, just it's not familiar, interpretation is more, is harder than optical data. So for this reason, we're combining that, we're fusing this, we take advantage of the optical sensor and also synthetic aperture sensor, and we're creating a flood map using the deep learning. So that can overcome the limitation of each sensor and work for the all-weather observation provide all-weather observation capabilities. So here also that can be very helpful for real-time data, monitoring of the complex environment. So we started with some testing in the Google Earth Engine using the machine learning algorithm. So we implemented and tested many different AI models, and we consider open water, dry vegetation, inundated vegetation. So just because the flooding and water has different behavior in the image, different color or different reflectance, depend on the different land cover and land use. So we try to consider that. And here is some example. This is the SAR vertical. VV is talking about the polarization. They have different polarization, and RGB, we use that three layer as input, and then we create, using the different machine learning algorithm, we get different results. As you see that they are very different. But based on the ground truth, we found that random forest is one of the most basically effective algorithm, machine learning algorithm for data fusion, and that using our data. But for making it more kind of helpful, we try to implement deep learning algorithm instead of machine learning. Still in machine learning, we need to human operator need still doing some engineering, feature engineering, but in deep learning, it's basically is data driven. So we can work with, provide the more reliable basically data, and we expect the reliable or meaningful the result. So here is the deep learning that we started to work. Again, we consider that different land use, land cover, inundated vegetation, dry vegetation, open water, and others, three different classes. We use both UAV and satellite imagery because we wanted to have a comprehensive study on the impact of the spatial resolution. And so we consider all those input. But one of the challenges that previously I mentioned is the label data. So one of the objectives for this NOAA funded project is creating the label data that we can use for the detecting flood in North Carolina, and can be used by other researcher or the our partner, or like public, for developing other method, kind of deep learning model for other states, or for other geographical study area. So for that, we use the pre-trained unit to create quickly a mask for the water, again based on our classes. And then we try to augment this mask and refine the mask and augment our information using different features like water index or SAR decomposition. So we put all of them together, combine them, and then we created another water mask that we a human expert basically corrected that to make sure that the result is correct. It's then to the quality control, and then we created final mask. That paper is under review, and hopefully when we publish, we make the data available to public, so they can use that data. Especially, I said, we have a lot of maybe training data set for open water, but not for vegetation. So the novelty of this work that we try to create label data for the challenging area like vegetated area, or the area that we have problem with occlusion. So here is the basically we try to use for implement deep learning for two Hurricane Matthew and Hurricane Florence in two different areas. So the reason that we trying to also test different events and also different study area, because sometimes we can collect data, develop method that work very well for that study area, for that event. But if you want to use that for the other area or for the other event, it might not work. So we try to work on also on scalability, and also we can transfer that what we're developing here to the other state, just and can be used with by the many other researchers as well. So here they're showing the result. As you see that the combination of UAV SAR, we had the flood mapping just only using UAV, only using the Sentinel tool that is the optical, but for satellite, and satellite optical and synthetic aperture radar, and UAV optical and satellite synthetic aperture data. So we try to develop different composition of the data and see that which one is better work for the flood mapping. And you see that always UAV and SAR working better. The reason because UAV is basically superior regarding the Sentinel-2 or optical satellite optical data for a couple reasons. First, UAV fly and under basically at low flight height, so that means we don't have the impact of the cloud on that. And then it's high resolution data. And then also SAR is fine. Even we can use satellite imagery. The reason because there is no impact of the cloud or like the sunlight on that. But yes, this is the what we receive as result, that UAV and SAR is best combination for creating flood map. But this is very even we had 8% for UAV in previous study. Still we found that this result, even the number is show lower, still is more effective. The reason because it could extract the flooding in the vegetated area as well. And so that means here we have 84% is vegetated and open water, not just open water. But as you see, we try to basically use our train model using the another basically flood during Hurricane Matthew in another study area, and you see that how much the accuracy basically reduced. So this tells us that when we're using a deep learning model, always we need to do fine tune with the data from that study area or from that event, even with the very small size of data, so we can have the good result for that deep learning. So here also is visualization of data. You see that it is the RGB, and that we have optical data using the basically aerial imagery, and here ground truth that is done through the human. Basically we did manually segmented data, and here is the result. As again you see UAV and SAR giving the best result comparing the ground truth. So this is the what we extracted from this research. And when we have the two-dimensional flood extent, if we combine with the digital train model, it can come from the LiDAR data, or can be come from the any other topography basically information, that if we overlay using some GIS data processing, we can basically make our map 3-dimension. So here we can have just also for each pixel of the flood map, we can have a elevation and showing that the depth of the flood water. Basically we have pre-flood DTM, we have water surface. Subtraction of these two give us the flood water for each point of the map.
Dr. Hashemi-Beni, I think you might be frozen. Okay, so we will give her just a minute to come on back. And while we're waiting for that, if y'all want to start typing some questions in the chat, please feel free to go ahead and start brainstorming what you want to ask. And then I will see if I can get things back up and running.
We found that deep learning algorithm, remote sensing, is very effective for data fusion, like just for creating accurate, fast, and automatic approach for environmental modeling and for the different natural disasters, including flooding. But what really we learned during those different research that we have done on that flood mapping, we found that flooding is really complex real world problem. Uh, it's maybe deep learning is not enough. Data alone can really be best alternative for physical modeling. We always need also include the information from domain, or we call domain knowledge, and detailed knowledge about the physical problem. So that means a hybrid solution is physics informed deep learning could be one of the best approach for environmental management, that we are moving forward to that solution. And also we found that even we need always to assess the performance of any AI or the data-driven algorithm in the different study areas, and also we can use that for the damage assessment and most kind of different impacts that flooding cause to human and environment. So just I want here acknowledge the help of my that I'm working with a big team on that. It's not my the research that I'm doing alone. A lot of undergraduate, graduate, student, postdoc are involved. Each of them contribute a lot. And also I would acknowledge the support of NOAA and North Carolina Emergency Management and SECOORA that really has been very helpful for this project. Thank you for very much for your time. Please, like if you have any question, I would be glad to answer.
All right, thank you, Dr. Hashemi-Beni. We do have a few questions coming in the chat. I do want to let everyone know that I'm going to allow, you can turn on your microphone and you can turn on your camera, so that if you'd like to pop on and ask your question face-to-face, you're totally welcome to do that. Or if you're more comfortable typing your question in the chat, you can do that as well, and I will read it out. So like I said, you should be able to turn on your mic and your camera now, but we do have a few questions. So we have a question from Felix Jose that says, can we get flood depth from LiDAR data itself?
Thank you for the question. Actually, it depends on the LiDAR, right? So LiDAR normally is a signal absorbed by water. Sometimes we use LiDAR for flood mapping because we get void in the basically wet area. LiDAR signal is absorbed, but we have some kind of other technology like bathymetry that using that different basically range of the laser, so they can penetrate to water and get the basically they can map the what kind of flow, right? So we can get that, like maybe we can estimate the water depth. But LiDAR alone basically can provide directly can provide the information, but unless you like we get the LiDAR pre-flood, that what we have done and used and intersect with the water surface and create water depth.
Perfect. Okay, so I have another question from Theo Yas. How do you account for dynamic changes to the stream bed that might occur during a severe flood?
Yes, that is a very good question. Actually, remote sensing is great for detecting flood, but um, is not. It doesn't do modeling. When we want to use like when we want to use remote sensing for modeling, we need to basically doing the data assimilation using the hydrodynamic, like just those strong model that define the basically fluid flow, right? Basically, remote sensing just capture one state of what's happening right now. So we get that maybe if we have continuous data collection, maybe we can do that. But remote sensing limitation is that just they can provide the information and one time step stamp at like just not continuous data. So if this answer your question. I think you are muted, Emily.
Thank you for that. Okay, so I have another question from Theo. Does the flooding detection algorithm only work with aerial top-down imagery, or does it work from lower elevation and oblique angle photos?
Yes, that is a great question. Actually, one of the advantage of using drone is not necessarily we need to do always top down. But when we're using the multi-view, like oblique data or collecting data from other view, maybe just it involve more complex mathematical model just for georeferencing. A structure from motion is one of these algorithm that is used by many software like Pix4D or Agisoft that it allow to get the data also not really vertical. You can have also oblique data or multi-view kind of imagery, but just it's involved more computation.
All right, so does anyone have any more questions? You can give it a minute. You are welcome to type your question into the chat. If you're having any issues unmuting, let me know in the chat and we can get your questions answered. And while everybody is thinking of questions, I just want to thank you so much for speaking during our webinar series today. I do want to call out that we do have a Drones in the Coastal Zone community of practice, and I think that it's really cool that we're bringing in some drones content to our SECOORA webinar series. So thank you for bringing that in.
Thanks for having me.
Yeah. All right, so I think our questions might have been exhausted. Do you have any last parting comments that you would like to make, Dr. Hashemi-Beni?
No, thanks so much. It's great to, I appreciate the opportunity and it's great to be connected with SECOORA and looking forward to attend other seminars that you have.
Yes. All right. Well, we appreciate you so much, and we appreciate everybody for attending today, for taking some time out of your lunch hour, and I will give you 15 minutes back.
Hey, Leila, it's Jennifer. I did unmute, so I wanted to say hey real quick.
Hi, Jennifer. Actually, maybe you also need to join us because you are one of the co-PI for this project,
No, you did great.
Thank you. And same for
That's
Gary, like Gary your support, working with you all is great. And we could get those results because of all of you.
Well, I think you did a great job on the talk. I saw Sandy LaCourte also gave you some kudos. She said great talk. I saw a couple messages pop up.
Thank you.
And I'm pretty sure Emily told you this was recorded and we'll put it online. So we usually have a pretty good number of folks that come back and hit the talks later too. So yeah.
Yes, I will send out the YouTube link to everybody that attended today, and it will also be released on our social media accounts. All right. Well, I hope everybody has a great rest of their Tuesday and a great long 3-day weekend coming up. And I will see everybody later.
Thank you all.
Thanks, Leila.
Thank you.
Thank
Bye-bye.
you. Bye.